Okay, welcome everyone. This is the first seminar for 2023, Fleet Seminar for 2023, and we're lucky to have Larry Liu along to present this first seminar. Larry is a professor at the School of Engineering at ANU, Australian National University. He's got a whole suite of publications to his name, and I'm not going to list them all, but he has just got a recent one in Nature. And he seems to have a few other side hustles or extracurricular activities along the lines of Outstanding Supervisor Award for the 3-minute thesis. And he's got the ACT Young Tall Poppy Award for Media and Outreach in 2016. But I'll let Larry introduce himself proper and start the presentation. Thanks, Larry. Over to you.
Thank you, Jason. Hello, good morning, everyone. Thank you for coming. It's a great honor to be here to talk about our recent work, the enhanced interaction of interlayer excitons in freestanding hetero-bilayers. So in this talk, first part, I will introduce the motivation and background related to interlayer excitons in van der Waals heterostructures and also the Moiré interlayer excitons. So next, I would like to focus on our recent work, the enhanced interactions of interlayer excitons in freestanding hetero-bilayers. So in this work, I would like to highlight two aspects. The first one is the reduced dielectric screening from the hetero-bilayer structure. The freestanding hetero-bilayer structure can lead to a highly enhanced formation efficiency for the interlayer excitons, which allow us to observe the Moiré interlayer excitons at room temperature. So the second aspect I would like to highlight is actually the reduced dielectric screening can also enhance the dipole-dipole interactions among the interlayer excitons, which allow us to observe the strongly correlated interlayer excitons and the formation of the interlayer Bi-exciton states. So at the end, I will summarize the talk and briefly talk about the vision. So here I would like to borrow a short video from Fleet to show the motivation and also the importance of interlayer excitons. Particularly, I would like to highlight the importance of the the exciton transistors. In the exciton transistor, 2 layers of semiconductors will be used. One layer contains electrons and the other holes. An electron and a hole will bond together to form an interlayer exciton. Collections of the interlayer excitons can condense into a superfluid. The flow of the superfluid can carry electric currents in the opposite direction in the top and bottom layer. So in the past decades, scientists successfully generated interlayer excitons in the coupled quantum-aware devices. So the challenge was the binding energy of those excitons in those 3-5 semiconductors was very low, typically in the range of a few millieV. So those excitons can only survive at low temperature below 10 Kelvin, for example. So recently, the emerged monolayer semiconductors can host tightly bonded excitons with binding energies in the range of up to around hundreds of millieV. So those excitons can survive at room temperature. Also, people can stack 2 different types of monolayers together to form a heterostructure, for example, here. From the photoluminescence spectrum and from the heterostructure regime, people can see the pure emission from the intralayer excitons that are shown up in the monolayer parts. At the same time, at the low energy regime, people can also observe an additional peak from the heterostructure area only. And this additional peak did not show up from the monolayer regime. So this additional new peak was assigned to be from the interlayer excitons in the structure. So in this specific heterostructure made up of MOSE2 and WSE2. So there's a type 2 band alignment. So when an electron and hole pair was generated in the first layer, for example, this WSE2 layer, then the electrons can quickly transfer to the other layer, and then interlayer excitons can be formed. On the other hand, when the electron hole pair was generated in this MOSE2 layer, and then the hole can also transfer to the other layer quickly to form an interlayer exciton. So an interlayer exciton is an indirect exciton because the electron and the hole are sitting in different layers. So their lifetimes are highly enhanced comparing with that from the intralayer excitons. And also you can see an interlayer exciton has a vertical dipole. So those interlayer excitons can show a very strong and long-range dipole-dipole interaction. So those strong dipole-dipole interactions can drive the whole system into many different quantum phases like superfluidity and so on. And also the photoluminescence, the PO emission from those interlayer excitons are very sensitive to the twist angle in the stack. For example, from this chart, we can see that when the twist angle is close to 0 or 60 degrees, then we can get the maximum quantum yield from the interlayer exciton emission. When the twist angle increases, and then this quantum yield drops dramatically. So this is because with a twist angle, then the interlayer exciton will become indirect in the momentum space as well. So in those cases, the interlayer excitons are indirect excitons in both real space and K space. So that's quite interesting. And also the in the TMD hetero-bilayer structure, Moiré-trapped lattice can be formed. And these days, people can use high-resolution image techniques to visualize the Moiré-trapped lattice. For example, here, people can use high-resolution TEM to visualize the Moiré-trapped lattice here. So we can also use this equation to precisely determine the period of the Moiré-trapped lattice. So the period is sensitive to the twist angle and also the lattice mismatch between those two layers. So when the twist angle is 0 or 60 degrees, then the Moiré period will show a maximum value. And this value is determined by the lattice mismatch of those two layers. In a TMD heterostructure, typically this maximum period is in the range of a few nanometers up to around 20 nanometers, depending on the materials we're gonna use. On the other hand, the Moiré-trapped lattice can also introduce a very interesting phenomena, the periodic energy landscape, energy potential landscape. So from this schematic, we can see that this is a twisted hetero-bilayer structure. So the green diamond shows this unit cell of the superlattice. There are three interesting regimes, A, B, and C. So from the top view, we can see that they show different stacking configurations in the A, B, and C. So this different stacking configuration, these two are different interlayer distance. For example, the D value in area A is the largest, and then in the area C is the smallest. This tiny amount of the variation in the interlayer distance can introduce a large amount of the modulation on the energy band gap. For example, here, the energy band gap could be modulated up to around 100, more than 100 millieV. So this energy gap is strong enough to trap interlayer excitons and also the intralayer excitons as well. And also the periodic energy landscape is also very sensitive to the stacking type in the heterostructure. In the TMD heterostructure, there are two types of stacking pattern, the R type and H type. For R type, the twist angle is close to 0 degree. For H type, the twist angle is close to 60 degree. So this is the calculated energy landscape for specific TMD heterostructure made up of WS2 and WSE2. So from this R-type heterostructure, so we can see this is the unit cell of the Moiré-trapped lattice. From this unit cell, we can see that there are two traps within a one unit cell. The main trap at location 2 and a second trap at location 1. on the other hand, if you look at the structure for H-type stacking, so from this unit cell, we can only see a single trap located at position 2. So that's the key difference between the R-type and H-type stacking. So these days, people have already observed Moiré-trapped interlayer excitons and Moiré-trapped intralayer excitons. Those results were published in past few years in Nature papers. Excuse me. So I need to highlight that actually in the TMD hetero-bilayer structure, the periodic Moiré potential could be easily affected by the surface states or the interfacial states. So that's why people need to use HBN layer to encapsulate the hetero-bilayer to keep the periodic Moiré potential. But the problem was the HBN encapsulation can introduce a large amount of dielectric screening to the system. And then this dielectric screening can reduce the formation efficiency of the interlayer exciton. So that's why the interlayer excitons were only observed at a cryogenic temperature. At the same time, this dielectric screening can reduce the dipole-dipole interactions among the interlayer excitons. So that will prevent us to observe some interesting phenomena from the system. So here in our lab, we fabricated a freestanding hetero-bilayer structure. So the freestanding heterostructure can prevent can reduce the surface state. At the same time, it can reduce the dielectric screening. This would allow us to look at the interlayer excitons, the intrinsic interlayer excitons in the hetero-bilayer without any additional dielectric screening and other effect. So in experiments, we use the dry transfer method to prepare a heterostructure and then transfer the heterostructure across a microscale hole. Those microscale holes were patterned using optical lithography and etching steps. So from the microscope image, we can see here, so this hole was covered by a hetero-bilayer structure. And so from this sample, we can always have two parts of samples. We can probe the freestanding part. At the same time, we can also probe the heterostructure on top of the silicon dioxide as a comparison. So in experiment, we use the photoluminescence spectroscopy to probe the emission from the intralayer exciton. So at room temperature, we can see here from the suspended structure, we can clearly see the PO emission from the intralayer excitons from the monolayer regime and also from the monolayer sample. At the low energy regime, at the low energy side, we clearly see a PO emission from the interlayer excitons. So this interlayer exciton peak was only observed from the suspended regime, but not from the supported sample area. I will come back to this later. So here, if we can zoom in to look at this interlayer exciton spectrum, we can see multiple peaks, and then we can use a fitting way to Lorentz fitting to show there are 3 interlayer exciton peaks. So in order to understand the origin of those 3 interlayer exciton peaks at room temperature, so we so sorry, I need to highlight this. This is a sample 1 I want to present here. For sample 1, the twist angle was measured to be around 0 degree, and then the Moiré period was extracted to be around 8 nanometers. Okay, here. So in order to understand the origin of those 3 interlayer exciton peaks from the freestanding area, so we ran a temperature-dependent PO measurements. So from this temperature-dependent PO measurements, we can clearly see that when the sample was cooled down, and then the interlayer exciton emission peak increased dramatically. On the other hand, the PO emission from the intralayer excitons, for example, those peaks decreased dramatically. So that's why at low temperature, the interlayer exciton emission peak became dominant in the PO spectrum. You can see here. And also so at room temperature we can fit we can use three peaks to fit this interlayer exciton emission spectrum, and at low temperature, so the third peak disappeared, and we can only see 2 peaks here. So this peak is consistent with the Moiré-trapped interlayer excitons reported before by another team. So they use the optical waves to confirm the Moiré-trapped interlayer exciton emission at this position from the same material, the WS2 and WSE2 heterostructure. So we can assign this peak to be from the Moiré-trapped interlayer exciton. And then based on this temperature-dependent measurements, we can also assign the 3 peaks we observed at room temperature to be from Moiré-trapped interlayer excitons. So for the first 2 peaks, IX1 and IX2, they can be assigned to be from to be trapped at the main trap here, the RHX, which is corresponding to the position 2 in the unit cell. And then the third peak, IX3, is the interlayer exciton trapped at the second trap at location here in this way. The energy difference between the IX1 and IX2 was attributed to from the spin orbital coupling induced energy splitting in the conduction band of the WS2 layer. Okay, here I would like to talk about the formation efficiency of the interlayer exciton. So as I mentioned earlier, at room temperature, we didn't see the PL emission from the interlayer exciton peak. But when we cool down the sample to low temperature, we can start to see the PL emission from the interlayer excitons from this supported sample area as well. But the overall intensity was much lower than the PL intensity from the suspended sample area. This is the absolute, the integrated PL intensity. But here, in order to exclude the collection efficiency from the supported area and also the suspended area, then we define a parameter here, the beta. So beta is defined to be the intensity ratio between the interlayer excitons and the intralayer excitons. For example, in each PL spectrum, we can integrate the interlayer exciton peak, and then so we can make the ratio and also integrate the PL emission from the intralayer exciton as well. Then we can extract the beta value, and then use this ratio to plot. We can plot the beta as a function of the temperature. So this plot can exclude the collection efficiency difference on those 2 spots. So from this chart, we can clearly see that the beta value from the suspended regime is much larger than the supported regime. So this suggests that the freestanding sample can give us much higher formation efficiency from the interlayer exciton. This could be due to the reduced dielectric screening. So in order to further confirm this trend, we also fabricated more heterostructures on different types of substrate with different screening effects. So here we fabricate 5 scenarios, 5 different types of samples with 5 scenarios. So here in scenario A, that's a freestanding heterostructure. So here epsilon 1 and epsilon 2 is a dielectric constant on top and also the bottom of the heterostructure. So this is the freestanding sample. And then scenario C is the heterostructure sitting on top of a silicon dioxide. The top is vacuum, is air, and this is silicon dioxide. So here, so for scenario C, D, and E, we made this type of sample. So we within a heterostructure, we can use HBN to encapsulate part of the sample, and then we can fabricate 3 types of samples. For example, here in scenario part C, it's sitting on top of silicon dioxide, and then so in D, it's sandwiched by HBN and silicon dioxide. In E area, so this sample is sandwiched by 2 HBN layer. So, and then we can plot out the beta value, the beta ratio. So here in this chart, we can normalize the beta value always to the sample sitting on silicon dioxide. So in this way, we can exclude, okay, the influence from the twist angle because we are measuring the same sample. So if you compare C, D, and E, you can clearly see here. So the sample area C has the largest beta value. And then if we compare the area, the freestanding sample, the A and C, okay, from the other sample, we can see the freestanding area has larger beta value. So for the B scenario, we made this type of sample. We try to transfer a sample across the hole, but by accident it was broken. So then this area was left on a PDMS, the J film. So then we can measure the beta value between this area and this area. So we can clearly see that from B area, the beta value is much higher than C. So then in this chart, we can clearly see that the lower dielectric screening can really introduce a much higher formation efficiency for the interlayer exciton. So this is consistent with the theoretical prediction, because if we reduce the dielectric screening and then the wave function of the electron and hole can show more overlapping, then this can enhance the transition possibility for the interlayer exciton. So this was the first time for us to observe the experimental evidence to show that this dielectric screening can really increase the formation efficiency of the interlayer exciton. This is very important for the second part of the result I would like to present. So here I would like to summarize the key factors that can affect the formation efficiency of the interlayer excitons. So as I showed earlier, actually the formation efficiency of the interlayer exciton are sensitive to the twist angle and temperature. So the lower the temperature, the higher the formation efficiency. The smaller, if the twist angle is close to 0 or 60 degrees, then the formation efficiency can be also enhanced. Now here we demonstrate that the third parameter could be the dielectric screening. So when we reduce the dielectric screening, we can also increase the formation efficiency. So as mentioned previously, people need to cool down the sample to very low temperature to see the interlayer exciton emission. But how to increase this temperature? If you want to increase the temperature, you need to optimize the other two parameters. Yeah. So that's what we did. So here in our freestanding sample, so the dielectric screening has been optimized. Now what we can see is here in this chart, we show the maximum temperature at which we can see the interlayer exciton emission. So from this sample with a twist angle of 15 degrees, we need to cool it down to 83 Kelvin, and then we can see the interlayer exciton emission. And then if we reduce the twist angle from 15 to 10 to 3 and to 0, we can clearly see this maximum temperature will be raised up from 83 Kelvin all the way up to room temperature. That's because in this sample, we optimize the dielectric screening, and also we use the twist angle is close to 0. So that's why this allows us to observe the interlayer exciton emission at room temperature. Okay, next I would like to talk about the second aspect. The reduced dielectric screening in the freestanding sample can also enhance the dipole-dipole interaction. So in the hetero-bilayer structure, there are two types of dipole-dipole interaction. The repulsive dipole-dipole interaction and the attractive exchange interaction. So when those two interlayer excitons are far away from each other, then the repulsive dipole-dipole interaction will be dominant. So if you look at the average energy of the system, then if the distance decreases, then you can see the average energy of the system will show a blue shift due to this repulsive interaction. But when those two excitons are close to each other, close enough to each other, then the attractive exchange interaction will become dominant. And then this attractive interaction will reduce the average energy of the system. And then eventually it will bring this energy from positive value to a negative value at this point. And then those two interlayer excitons can bond together to form a robust interlayer Biexciton state. So actually the Biexciton state was predicted in theory decades ago. From this chart, you can see here, this is the Biexciton phase, but it was never reported in experiment before. So that's there are two possible reasons. For example, in the double quantum aware structure, from this chart, we can see here, if you want to see the Biexciton phase, you need to make sure the d value, the interlayer distance d value is smaller than the average size of the interlayer exciton. So in the conventional quantum aware structure, it was very difficult to make a small d value. So that's why people didn't observe this kind of bilayer interlayer Biexciton from the coupled quantum aware structure. So these days, the hetero-bilayer structure from 2D molar layers can easily meet this requirement. But before, people didn't observe this interlayer Biexciton state. That could be due to this kind of strongly highly enhanced dielectric screening effect. Okay. So here, the freestanding structure will provide a very interesting platform to look at the dipole-dipole interaction. So in order to look at the dipole-dipole interaction, we did a power-dependent PO measurement, and then we can track the peak position of the interlayer exciton emission. So from the supported sample, this is still from the sample 1 with a twist angle of 0 degree. So from this supported area, we can see that the PO emission from the first peak, the interlayer exciton peak, show a blue shift when we increase the pumping power or increase the exciton density. But from the suspended sample area, we can see that this blue shift is not linear. It shows a nonlinear dependence. So when the pumping power was a bit low, we can clearly see the blue shift. But in the second range, this slope was much lower than the first stage. And then we can clearly see it will saturate some values. So how to understand this nonlinear dependence? So for this data, we can use the mean field approximation model to model this blue shift. In this mean field approximation, we just assume, okay, all the interlayer excitons, there are no correlations. And then from this stage, we can also use the mean field approximation model to fit this blue shift, assuming that there's no any correlation among the interlayer excitons. And then this stage, it can also be modeled using this the mean field approximation model with a pair correlation correction. So based on the previous theoretical study, people also predicted this type of behavior. So for example, so when the interlayer exciton, the density of the interlayer exciton is very low, which means all the interlayer excitons are fully isolated. There are no any correlation among those interlayer excitons. Then we can use the mean field approximation model to model the system. So then this is the blue shift energy of the PO emission. And then this blue shift energy is linearly proportional to the density of the interlayer exciton. So from this equation, we can easily see that the linear dependence, if there's no any correlation among the interlayer excitons. But when the interlayer exciton density increases, then this assumption will be invalid. So we need to consider the correlations among the interlayer excitons. For example, the first correlation could be named as a pair correlation. So because the two interlayer excitons, they can collide with each other. But because of this repulsive interaction, so those interlayer excitons cannot, there's a minimum distance here are 0 between those two interlayer excitons. So this type of pair correlation needs to be considered when we try to model the system. So this is the equation for this pair correlation. So you need to use this pair function, correlation function, to correct this this shift. So for this pair correlation function, you can see here, in our case, this value was calculated to be around 0.1. So that's why this slope, the energy shift as a function of this exciton density, this slope was expected to be much smaller than the first slope. So that's why we can. So this model matches quite well with the experiment. So now you may ask, okay, why you can see two slopes here from the suspended area. So in order to figure out the potential reason, then we did exon diffusion measurements and then try to see, okay, what's the relationship between the exon density and this kind of exon correlation. So in experiment, we can image the exon diffusion by using the this space versus the energy mapping. So this X-axis, that's the emission energy, and then Y is the space. So here we can draw a line cut, and then we can plot out the pure intensity versus the space. So here, this the blue dot. So sorry, the black dots shows that's the laser profile. And then when we increase the pumping power or increase the pumping the exon density, we can clearly see that when the exon density was low, then we cannot see any diffusion because this line overlaps with the laser profile. But when we increase the exon density, we can clearly see this line start to show some sort of diffusion, so sort of exon diffusion. And then at a very large pumping exon density, then you can clearly see a large amount of exon diffusion. So this could be understood by the following picture. So when the exon density was a bit low, then most of those exons will be trapped by the Moiré potential. Then those traps can prevent the exon diffusion. But now if you increase the exon density, then the repulsive interaction among those interlayer exons would be strong enough to overcome the energy barrier, and then some of those exons can hop out of the energy trap, and then you can start to see the exon diffusion. And then particularly if you look at the value here, this value is around 1 to 2 times the 10 to the 11. Yep, that's the value. So this value is roughly similar to this value. You can see here, this is a constant, which means in this stage, okay, in stage 1, most of those interlayer exons were trapped by the Moiré potential. And then in stage 2, it looks like the interlayer exons start to diffuse because the repulsive interaction would allow those exons to hop out of the traps. And then you can see those kind of diffusion. So this diffusion would allow those exons to rearrange their location. So this can reduce the overall energy of the system. So, and then it can introduce some pair correlation. Yeah. So here we can also use time-resolved photoluminescence to measure the lifetime of the interlayer exon. So from this sample 1, the lifetime was measured to be around 10 nanoseconds. Actually, the lifetime exon density of the interlayer exon is a very important parameter to probe the correlation and also the dynamics of these interlayer exon. So how to control the exon density is very important. So the density of the interlayer exon is proportional to the pumping power when we use a CW laser pumping. And also it's proportional to the lifetime of the interlayer exon. So in order to increase this exon density, you need to increase, but we cannot use a very high power because to avoid this potential damage to the sample. But on the other hand, you can increase the lifetime of the interlayer exon. So then you can also increase the twist angle in the heterostructure. When you increase the twist angle, you can increase the lifetime by 1 to 2 orders of magnitude. This has been demonstrated before. So which means you can use the heterostructure with a large twist angle. But there's also a trade-off, the problem. So when you increase the twist angle, then the quantum yield of the interlayer exon will drop dramatically. So that's why people would not be able to see the pure emission from a hetero-bilayer with a large twist angle. But now here, so actually in experiments, we can also use the, here we can make a freestanding sample because the freestanding structure will allow us to enhance the formation efficiency of the interlayer exon. So then this would allow us to probe some heterostructures with a very large twist angle. So that's why in experiment, we fabricate different types of samples with different twist angle. And also we can use the second Second-Harmonic-Generation angle resolved SAG to determine the twist angle between those two layers. So for example, here, this is a zero twist angle sample with zero twist angle with 3 degree. So this is the 45 and this is the 51 degree. So here, for the first two sample, it belongs to the H-type stacking, and then for the second two sample, those two samples they belong to the H-type stacking. How to determine if it is R-type or H-type in the SAG measurement? So typically in the R-type stacking, the SAG signal from the heterostructure will be enhanced comparing with the monolayer structure, monolayer. On the other hand, from H-type stacking, so the SAG from the heterostructure will be quenched comparing with the monolayer structure. So using this way, we can identify both the twist angle and also the type of stacking. Okay, so in experiment, we also probe a second sample with a twist angle of 51 degree. Okay, so this is the second sample. We use the power-dependent PL to measure the interlayer excitons from this sample at 83 Kelvin. So at low temperature, we can clearly see two emission peaks at the low energy side. Those two emission peaks belongs to the interlayer exciton emission from the heterostructure. So we can only, from this sample, we can only see the interlayer exciton emission from the suspended area part, but not from the supported area part, even at low temperature. And then we also measure the power-dependent PL measurements. From when we increase the pumping power, you can see here the high energy peak became dominant, increased dramatically, and then finally it became dominant in the PL spectrum. Actually, the most interesting part is here we also plot out the energy of those two peaks. From the first peak, the low energy peak, it always shows this kind of repulsive or blue shift. But from the second peak, the IX2, we can clearly see that it showed a blue shift and then followed by a large amount of red shift. So this was the first time to observe the repulsive and the attractive interactions among those interlayer excitons. How to understand why we can see those kind of attractive interaction? So in order to figure out the region of those interlayer excitons, we also did a temperature-dependent PL measurement. So at low temperature, we can see two peaks, IX1 and IX2. But when we raise up the temperature, the IX1 disappeared at when the temperature was above 173 Kelvin. But the high energy peak, IX2, can always survive all the way down up to room temperature. So based on our analysis, we can assign this interlayer exciton 1 is coming, could be from the Moiré-trapped interlayer exciton, and the IX2 could be from the free interlayer exciton. So please be noted that this is a H-type stacked heterostructure. From a H-type stacked heterostructure, as I mentioned earlier, there was only one main trap in the lattice. And also for this sample, because the twist angle was measured to be 51 degree, so the Moiré period was extracted to be around 2 nanometers. And then this is the period. So then the size of the trap was around 1 nanometer, which is very close to the size of the interlayer exciton. So this means that each trap can only probably trap a single interlayer exciton. And also based on the measurement data, the energy difference between the IX1 and the IX2 was measured to be around 90 milliV, which is very consistent with the calculated the trap potential, the depth of the traps in this H-type structure. Okay, here actually, based on the power-dependent measurement, I would like to also highlight that. So from the IX1, it shows the slope, the power dependence shows a slope smaller than 1. And then this slope for the IX2, it shows a superlinear power dependence. this superlinear power dependence might suggest that the IX2 could be a mix of the single layer interlayer exciton and the interlayer Biexciton. So, but here in this sample, because the bandwidth or the line width of this IX2 was a bit large, so that's why we were not able to identify those two peaks, from the single peak and also the Biexciton peak. Okay, so in order to look at the if we want to identify or those two peaks, you need to make sure the line width of this peak is narrow enough. So in this sample, because of this Moiré potential, the landscape, so actually the scattering mechanism is large. So in order to minimize this scattering induced by this landscape, we fabricate a third sample. For this third sample, the twist angle was measured to be 45 degrees. And then based on the calculation, we can extract the Moiré period to be around 1.2 nanometer. And then the trap size was estimated to be smaller than 0.6 nanometer. So in this sample, then, which means the trap size was smaller than the interlayer exciton size, the size of the interlayer exciton. So in this case, which means we would not be able to see the Moiré-trapped interlayer exciton from this sample. That was exactly what we observed from experiment. From this sample, you can see at low pumping power, you can see this is the interlayer exciton peak. You can see a low energy interlayer exciton peak at an energy of around above 1.5 electron volts. So this energy peak is consistent with, is close to this high energy peak IX2. So from this PL spectrum, we didn't see a low energy peak at this energy side, close to IX2. So which means this interlayer exciton is, this IX peak is coming from a free interlayer exciton, but not from Moiré-trapped interlayer exciton. Okay, so from this large peak, we can also see multiple peaks under a high large power pumping. At a low pumping power, we can see only a single peak. But when we increase the pumping power, we can clearly see from the low energy side, a new peak emerged and then became dominant in the PL spectrum. On the other hand, on the high energy side, we can also observe another peak IX2 here as well. So there are three peaks in the PL spectrum, and we label it as IXX, IX1, and IX2. So how to assign the origin of those three peaks? So based on the analysis, we can assign this energy peak, the low energy peak, to be from the interlayer Biexciton state. And then those IX1 and IX2, they are from the free interlayer exciton state. So this assignment was evidenced by the following signature. So here we show four signatures about the interlayer exciton, the interlayer Biexciton states. So firstly, if you look at the power dependence, okay, so for IX1 and IX2, the power dependence, the power law is close to, was measured to be close to 1. So this suggests that the IX1 and IX2 are coming from interlayer excitons. But on the other hand, this slope from the IXX peak showed a superlinear power dependence. This alpha value is much larger than 1. It was close to 2. So based on this power dependence, if the exciton, the power law is close to 1, which means the exciton could be from a single exciton. If this power law is close to 2, then which means the exciton could be from the Biexciton state. If the alpha value is smaller than 1, typically people can say they are from a defect or other states. So that's the first evidence to show that this IXX peak could be from the interlayer Biexciton. The second signature was the line width. So from the line width, we can see that this exciton peak, the line width from this IXX peak was measured to be around 2 times larger than this, that from IX1 and IX2. So this suggests that this also, this is consistent with the signature of an interlayer Biexciton, because the average size of an interlayer Biexciton is much larger than a single interlayer Bi-exciton. So that's why the line width could be much larger than the interlayer exciton. The third one is the energy shift. So from the IXS peak, we can clearly see this kind of repulsive and also attractive interaction. But from the IX1 and IX2, they only show this type of blue shift, which means they are those interlayer excitons showed repulsive interaction. The last signature was the binding energy. So the energy difference between the IXS peak and IX1 was measured to be around 16 milliV. So we can define this to be the binding energy of an interlayer Bi-exciton. So this measured binding energy was consistent with the simulated binding energy of an interlayer Bi-exciton. So the simulated value was around 15 milliV, which matches very well with the experimental value. So based on those four signatures, we can confirm that this is the IXS peak was coming from the interlayer Bi-exciton state. So here I would like to summarize my talk. So hopefully I convinced you that the freestanding hetero-bilayer will be a very interesting platform to look at the dipole-dipole interaction among the interlayer excitons. So those reduced dielectric screening can increase the formation efficiency of the interlayer Bi-excitons. That allowed us to observe the Moiré-trapped interlayer exciton emission at room temperature. On the other hand, this reduced dielectric screening can also allow us to probe the highly enhanced dipole interaction, which allow us to observe the interlayer Bi-exciton state for the first time. So finally, I would like to briefly highlight the vision. So this discovery in experiment can help us to understand the dynamics of the interlayer excitons and can help us to potentially to understand the dynamics for potential superfluid state. So actually exciton states, the traveling speed of excitons in traditional semiconductors is very low, similar to cars traveling in a city full of traffic. But a superfluid state could be visualized as a superhighway for excitons. And then this would allow us to generate next generation, to develop next generation low power and super fast information technologies. For example, exciton transistors, exciton circuit interconnects, and so on. All right, finally, I would like to acknowledge my lab members, my collaborators, and also the funding agencies. Thank you very much for your attention. I would like to take questions if you have. Thank you.
Thanks, Larry. For any questions, just unmute yourself and ask away. There's a question in the chat for you, Larry.
Okay, yeah. How does the electric screening affect interlayer exciton oscillation? That's a good question. So based on a theoretical calculation, the dielectric screening, so with a reduced dielectric screening, then the wave function between the electron and the hole will increase, and then that can increase the tunneling rate for an interlayer exciton. Then this can increase the quantum yield. So in terms of the oscillation strength, I'm not quite sure, to be honest, because in principle, people always say that for interlayer exciton, the oscillation strength is low. I think maybe the dielectric screening can really increase the oscillation strength a bit. That's my understanding, but I'm not sure if this is true or not. I'm not sure if this answers your question. Okay.
There's another question in the chat.
The second question. Okay, how does the interlayer exciton affect the optical nonlinearity of the material? Okay, that's a very good question. So the interlayer exciton, as we show here, first for if you look at the power dependence pure measurements. So here, if you increase the pumping power because of the repulsive dipole-dipole interaction among the interlayer excitons, then you can see the average energy of the system will show a blue shift, right? And then this can introduce the nonlinear behavior of the system, I believe. And also particularly if this dipole-dipole interaction is highly enhanced, then you can clearly see the strong correlation among those interlayer excitons. For example, the pair correlation and the quantum exchange correlation, as I showed earlier. So the quantum exchange correlation can introduce the formation of the Bi-exciton state. So those kind of correlation interaction among the interlayer excitons can introduce a large amount of the nonlinearity in the system. So I think that's the interesting part to explore for future device integration. I'm not sure if this answered the question. Okay, Alex, okay, thank you. What's the maximum lifetime of interlayer exciton? That's a very good question. So based on previous measurement, so for interlayer exciton, if the twist angle is close to 0 degree, the measured lifetime was in the range of around 10 nanoseconds, which was around 2 orders of magnitude larger than the intralayer exciton. Now, if you increase the twist angle from 0 degree to probably 10 or 15, so that lifetime could be increased to more than 100 or even 200 nanoseconds based on report. And also we've got very long lifetime as well in our experiment. Yeah. So in principle, I guess, so if you can well control the defect state, or if you can control the decay channel, so this lifetime might be increased into microseconds, I guess, but that was not reported yet. So it should be possible, I guess. Yeah. Thank you, Alex.
Any other questions for Larry?
Yeah.
Don't think so, Larry. Whoops. Oh,
okay.
It's we're hitting the air. Oh, hang on. Jack's got one for you in the chat.
What are your thoughts on the K gamma transition causing multiple peaks around the? Yes, that's a very good question, Jack. Thank you. So based on the okay, let me go to that. In this Nature Materials paper, actually, they claim actually the lowest transition for this material system, the lowest energy from the interlayer exciton is coming from the gamma, the K gamma transition. It's not from the KK transition. It's an indirect transition actually in the momentum space. So in our experiment, we didn't probe that in detail because we just cite that paper. So based on previous experiments, people really always observe that in some material, so the lowest interlayer exciton could be coming from the direct KK transition, but in some material system, for example, WS2 and WSE2, the lowest interlayer exciton is coming from the indirect transition from gamma K. In the momentum space, that's correct. So in this material system, but actually because the energy difference is not that large, so at room temperature or even at low temperature, you can still see a large amount of interlayer exciton transition because the energy difference between the gamma K and the KK transition is not that large. Yes, I'm not sure if that's the answer to your question, Jack. Yeah.
But could I also ask a quick question?
Sure, Anil, please.
Yeah. Thank you for the amazing talk. So previously there was some reports of hybridization between the interlayer and intra-layer excitons. Do you see some evidence of that in your hetero-bilayers, or do you attribute similar signatures to formation of
Sure, that's a very good question. So here it depends on the material. So if those two layers, for example, if this conduction band are close to each other, for example, if this level is close to this level, then in that type of 2D material system, heterostructure, you will be able to see the hybrid in interlayer exciton. So because the interlayer exciton, the energy of the interlayer exciton is very similar to one of the intralayer excitons, for example, in this material, then the interlayer exciton can hybridize with this intralayer exciton. So which means this electron can hop between this state and this state. So in principle, you can see a hybridized interlayer exciton. But in our material, we use WS2 and WSE2. So the energy level of this conduction band and this conduction band is a bit large. So that's why in our material system, we didn't see a hybridized interlayer exciton. Yeah.
Thank you.
No worries.
Any last questions before we let Larry go to lunch?
Let me see.
No, I don't think so, Larry. All right, look, I'd like to thank Larry a lot. Even a non-physicist like me got a little bit out of that one and enjoyed the talk. But look, Larry, thank you very much for your time. I'll be in touch with the recording link as soon as it does all its little thing behind the scenes. But yes, we'll chat soon. And thank you very much for that, Larry.